settings are okay, I suppose. Okay, so cluster validation. Okay, so we already had the centroid index video there, so you have pretty some idea of what the validation is about. So there was this kind of background, oranges and apples from classification. We can measure the classification accuracy because we know what is the correct class, that this is supposed to be oranges here and they're supposed to be apples here. So we can calculate precision and recall. Precision is that, okay, how many of the oranges we managed to capture in that class. And then precision is, precision is 100%. We get all the probability numbers are vice versa. I think this is recall is 75%. So we get 100% recall because all oranges were found, but the precision is not 100%, 71, because we have also some extra other items there. And vice versa, apple class, here we have, out of the 5 apples, we only find 3, so this is supposed to be, recall is 60%, so I think this is correct. And the precision 100%, no other classes. So there are two sides. If we put everything in the same class, we have always 100% recall, but the precision will be low. And vice versa, if we don't select anything, we have very low recall, 0 recall, but the precision is basically perfect because no false choices. Okay, but now this is a supervised classification or supervised learning. We know the ground truth and we even have the class labels, so we know how to measure. And in cluster analysis, no class labels, so we need to compare that how we compare 2 different clusterings. Whether one is a ground truth or just 2 different clusterings, how similar they are. Okay, this is in the one approach to compare. But now we are more interested in the case that we don't have any ground truth. We are not comparing any clustering result to some other clustering result, but we just have the single clustering result and we want to know how good is it. So going for the sum of squared, okay, the sum of squared error we already have. So no matter, no ground truth needed, we can always measure how compact are the clusters. So it's a measure of goodness. But then again, if we want to solve the number of clusters, which I emphasized here, this is the main reason we are using some other validity validation methods. We want to compare if I have 3 clusters or 4 clusters. And the more I have clusters, the more compact they will be. So it's like having all in one class, we have the perfect recall, 100% recall. It's the same. We put everything on cluster, we have zero variance, perfect size of clusters, but that's not the idea. So something needs to be solved here. So basically, how to compare clusterings of different sizes. And also without any external index. So if you have external index, then we can of course use centroid index or some other method to do it. Okay, basically, this I don't have much material and I don't really know how should we deal with it. But basically, if you have random data or just something that we have just some data, whatever distribution, but if there are no clusters. So our first task is basically to see, are there any clusters? And only after that we can start to ask how many clusters. Okay, basically we could make it just as a special case that, okay, yeah, just one cluster. Or why not, we have n clusters. So there are like 2 extremes. Which one should be the correct answer for this kind of case? 1 cluster, n clusters, because the answer is that there's no clusters, there's just data points. So how to deal with it? So in practice, typically the number of clusters questions are asking is that 2 clusters, 3 clusters, up to some upper limit. And the upper limit can be something at the ortho lane like n divided by 2, but more likely it goes some I don't know, usually square root of n is quite good initial guess if nothing else. So what is the expected number of clusters? So if you have there like, okay, WordSet has 100 clusters, but then again there are 100,000 of vectors and square root of that one is, I think it's 1,000. So it's within the limit. But yeah, so And if you apply the algorithm, you can see that, yeah, even with k-means, with this sum of squared criterion, it will find some kind of clusters. Other methods, complete link will find different clusters, DB-scan different clusters. So the algorithm doesn't know that there are no clusters, it just will find it. Okay, there are some step-wise details here. I will skip it. I hope that I talk it just was the same. Okay, another blah 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 definition by China and Dubes. How to be quantitative to employ the measures, how to be objective to validate the measures. Well, okay, I will skip it, but basically giving the data, apply to algorithm, and then validate what is the goodness of that. And then we just let's try different number of clusters and validate again. So this kind of a brute force approach with the parameter of the number of clusters, and so this black box validity index is what we need. Okay, so let me repeat just in case. So what we are going to do is to have 2, 3, 4 up to some upper limit, whatever, let's say k max number of clusters. Feed the data, so we have the data here, feed the data and feed the k into the clustering algorithm. Is it k-means or something else? That's the input, and then output we have the clusters. And then for these clusters, now we need to define so-called cluster validity index. I don't know how should somebody call it CVI, but anyway, we give some number out of it. And in simplest case, this is just sum of squared error. So that's what we are going to do. Simple approach. Let's try different numbers and then validate what's the result. So that's our black box, what we now need to define. Okay, so I consider this as two different problems. To find the clusters with the given data, given parameter, we just find it. It's an algorithmic problem. K means random swap, something else, we solve it, and we don't care about the result. And the number of clusters with this idea is completely different. It's just to have to measure that we are able to compare 2 clusters and 3 clusters. So it's a function, so it's like mathematical problem. And it comes originate from the reason that what we define as a cluster. So basically, if we put a bunch of points together, we have to define how good is this as a cluster. So the compactness variance is what the sum of squared error basically measures. The smaller the variance, the better. Okay, so that's the simple criterion, and then we apply that one. But yeah, clearly the more clusters, the lower the variance, so it's not enough. We have to balance. So if you have 2 clusters, or if you have 3 clusters of the same data, so now we have to keep some kind of penalty for the numbers. The more the numbers, so the compactness is not enough. So let's see. So now they are here listed some of the methods. Variance is, okay, the first one is variance of within cluster and between clusters is kind of the first idea to go beyond this within cluster variance. So this is a within cluster variance, so how compact is it? So then, in addition, let's measure how far, so the clusters, points in the cluster should be as similar as possible to each other, but points in the other clusters should be as dissimilar or as far as possible. So now if I take many small clusters, we will have one point here, another point here. The distance between these points with other clusters is quite small also. So basically we want to maximize this distance and minimize the distance inside the clusters. 2 contradicting goals, but yeah, that's what this is now. We want to find best possible compromise, and if there are real clusters in the data, if we have lots of points here, definitely if we put 3 clusters, there will be 2 clusters that are the between cluster variance is quite low. But if we put only 2 clusters, the between cluster variance is much higher. And the compactness doesn't change. If you put only 1 cluster, then the within cluster variance is also high. So it's quite sure that now with this compromise, maximizing the between and minimizing the within, so we will most likely that the two clusters will give. So there should be some mathematical function that basically have 2, 3, 4, whatever, that this function has minimized, that the minimum point is at the correct number of clusters. But it could be also maximization, so it could work opposite that we are looking at the maximum point. But that's what we want to define, and this first idea is kind of a general. It's if we can implement in practice, I think that will actually solve it. Yeah, so this is a little bit boring in a sense that there are just a bunch of mathematical approaches here, not so much interesting, but let's take a look at least some of them, how they are built up. Rate distortion method. This comes from image coding or data compression in general, idea that they are, like if you compress by JPEG, you know that you have a quality factor in JPEG. The higher the factor, the more bits in the file size and the better quality. And if you reduce the quality factor, the image will be more rough. Quality goes down, but also bits go down. Well, usually nobody really tunes this quality factor in JPEG. You're just happy what there is. But if you want some thumbnail, you could try this quality factor to get lower file size. Well, I usually just reduce the resolution, so it's so simple. But in principle, there is this kind of at least JPEG 2000 file format. It's already much clear that you can really compromise how many bits you allocate for this file, the better the quality. So it's a compromise. So the rate distortion theory is basically this, that you want to balance as a rate, how many bits you invest, and there's the distortion, how many error you allocate. But yeah, okay, I think it would be too difficult to study. F-ratio is a statistical test, and basically what I'm going to propose at some moment here, based on the first, it's also based on this one. It can be, it's basically generalization of statistical F-test. If you're familiar with that one, you can try to see if you can see the connection. And then many heuristic method, Davies-Bowden index, also bias and information criterion. One thing is you have to know that the cooler the name, more popular it will become. So this bias information criterion, yeah, it's for Gaussian mixer models mostly. So Gaussian distributions, it can model that one, and then it's applied here also for this kind of K-means clusters. But I don't think it works that well. So as long as you claim that it's based on some theoretical results, so people, how I want to. So I have concrete evidence with my PhD students in PHR. We have a nice paper about how to improve this method, this kind of find the key point of this BIC. I don't think it's that good method really. Yeah, it does improve, make it a little bit better, but there are better methods. But oh boy, people love it. People just really excited and start to ask details about it. I think, yeah. But what I can do, then I should invent some better method first to say that don't do it, it's not that good. But yeah, so that's one trend. The cooler the name, the more popular it will become, but it doesn't mean that it really works in practice. So this, yeah. See, like two different points. So there's this kind of a heuristic we have. Okay, it doesn't based on something mathematical or something, but it anyway has some cool name. So more like this kind of heuristic approach, and then try to rely on some theory. And minimum description principle. Okay, this I would say this has the most promise in my view, because in data compression, like this rate distortion here. So again, like the more clusters, the more compact it will be. It's the same. The more you invest a bit, the better quality it will be. Where's the compromise? Where's the minimum? There should be contradicting goals, and minimizing bits and maximizing quality. So yeah, okay, they are contradicting goals, but how do you measure? Because in JPEG and data compression, you just have to choose it yourself. There's nobody telling you that this is the this is the optimal point. There's no optimal point. You have to choose. But minimum description principle actually does, it's based on this kind of, yeah, okay, so this might refer to some certain mathematical simplified case, but also stochastic complexity. I think these together, third concept I'm familiar with is Kolmokov's complexity. Okay, so if you are familiar with any of these I described the idea briefly. So again, from data compression. So we have some data here, X, and what we want to do, we want to build model of the data, and then we want to code the data using that model, so that we have the kind of the compressed or coded data as output. And as data compressor, we want to minimize the file size. Now, the model here, it can be some code book, Hartman code or something, statistical distribution, or cluster center points, or some cluster models. It could be also variance or whatever. So this is some extra data that we extract from the information. Cluster here, cluster there, and cluster here. Now, so that the decoder can need to reconstruct the original data lossless, exactly original as such. So what it needs, this extra information must be transferred, so the bigger the model, the more space it takes. You have to store it in the file. You have to tell the other party that what is the model that you are using. And then you have to just use this model that, let's suppose I have a point here. So instead of sending all the attributes of this point, I could say that first I send index. This point belongs to cluster 3. Okay. If I have 3 clusters, how many bits I will need? So I claim that 2 bits is enough if I code this 0, 0, 0, 1, 1, 0. Or in general, logarithm of the number of clusters, bits. Okay, no minus here, just logarithm number of bits will do. Entropy, Shannon's entropy, so it will give the number of bits. So telling the first that this belongs to that cluster. Okay, then next. Okay, what is the so-called predictive coding, that instead of like lossless JPEG, for example, it doesn't use any DCT, discrete cosine transform, or any complicated theory, but it does take 2 pixel values of each other and take the difference. And instead of coding the original values, it codes the difference, because expected that the values doesn't change that much, so the previous will predict. And most values will be around 0, minus something, plus something, but the distribution is not random, it's usually like that. And this distribution has entropy much smaller than the random distribution, and this can be coded. Smaller code length for these low values and the bigger ones, bigger code. Okay, principle of coding. So the idea is that in clustering we could now code this single point by 2 things. First we code what cluster you belong to. Couple of bits to tell the index. Okay, you are cluster 3. Okay, we have to tell the clusters, of course, like the prototypes. What are the centroids? Okay, this is a male. This is average height is 177. Driving car Ford. I don't know, average car, whatever. This is more difficult. But basically, we code the information. What is the clusters? And next thing we will do that our cluster prototype is here. This we know. This we store it in the model. So what we now need to do is code the difference from our point to the model. And if we just tell our data space is here, if we code what is the exact attribute, you have lots of choices, but the difference is just okay. Your average age is 177 in this cluster, and you are 175. So you have to code number -2. So okay. So now after that, the idea is that we try different clusters for different number of clusters, because the more clusters, the bigger the model. This will take more space, but the more better predictor we have, and the actual coded data will take less space. And what we want to find out, the best compromise that minimize the total file size. So if we have clear clusters, so this correct number of clusters, that number of clusters is expected to produce the minimum file size. So all of this minimum description principle, stochastic complexity, and if there are some others, they are based on this kind of principle. So find the best model size that we can minimize the coding. Okay, now I'm backing off a little bit. Let's go back to the where we started. So we started with the sum of squared errors. Here I still have the MSC, but the sum of squared errors. Okay, this seems to be S2 data set. So the more clusters we add, you can see that this goes down. And yeah, so we can't use it as such. But okay, first people notice, aha, but there's a key point. Many people are immediately able to see that, aha, it goes down like that, and then it suddenly turns like that. Yes, there's a key point, is it? Well, okay, that's it. Well, yeah, okay. I just basically correct. There might be key point, but in many cases you don't see it yourself. And even if it's there, if the key point, if it's like that, if there really is key point, yeah, we can detect it actually quite easily, just by taking the differential. Because difference between two values is, in this case, let's suppose it's -2, -2, -2, -2, here, 0, 0, 0. So we can translate this actually -2 and 0. So the new signal would be at -2 and then 0 level. Okay, we still have to detect this point. Okay, let's take second derivative. Second derivative of that, okay, difference here to here. Okay, 0, 0, 0, 0. Aha, here is a +4 or something. Here, 0, 0, 0. Now we have function that behaves like that. Yes. Find the maximum and that's it. So it's yes, we can actually go from SS sum of squared errors, these variances, find out where it actually have this kind of sudden changes. And yes, this is one of the first ideas. But then how in practice? Okay, even if data we have clear clusters, now we have come second. The one is, yes, there are, okay, how many clusters? There? Not 5? Well, somebody color it, so the person who colored it thinks that there are 10 clusters. But yeah, if you look the curve, yeah, there actually is a key point, but there are actually 2 key points. One is at the 5 clusters and second is the 10 clusters. And if you look carefully, which of these key points is bigger if you take the second derivative? Yeah, I think here's a much more sharper turn, so most likely there will be a bigger peak here and there. But yeah, basically it recognizes 2 peaks, so it's possible. Then again, this, I don't know what this example is supposed to illustrate, but there are clusters, there are random noise at the background. Now I'm not even sure what this is now measuring, but yeah, I think there are 7 clusters. Okay, 1, 2, 3, 4, 5. Oh, okay, I give up. I'm not sure what's going on with this picture. Okay, but now back where I started. So okay, so key point is one idea. Second is this intracluster versus intercluster. So minimize what is inside the cluster and maximize between the clusters. So how to do it? Oh, this is very jumpy now. We have a suddenly method that goes back to the derivative ideas. Okay, so this is, okay, they tend to be a rate distortion approach. I have no idea how it relates to rate or distortion or anything, but the actual equation is based on the total squared errors of with k clusters, k minus 1 clusters, okay, take 2 subsequent. So basically, and take the difference, derivative, clearly derivative. Only difference is that now this is taking your exponent, so this is a power x by dimensions, how many attributes you have, divided by 2. And that is taken minus. So this minus is basically if you have a x minus something, so this is basically the same as 1 divided by x or some y, right? So it's basically takes the inverse of the squared error. So first you take scale it and then power and then take the difference. Okay, I can't say what exactly does it do, but it does find a clear peak here. Now, if I only knew which data this is, because 15 clusters is supposed to be here, so yeah, either it finds the wrong place or there's something fishy on this picture. Okay. Like I said, I don't have much of practical examples how these measures behave in practice, so this is a little bit waving in the air or guessing what's happening, just giving the intuition. Okay, but let's go for the next. This is the one that I recommend in the sense that, okay, I don't have the final result. I have been ideas in my head already a long time, many years. And waiting I could really work on it and make it through. So before I get it, the final solution, if there ever will be any final solution out there for you to have, the second best, I don't know, is this even the second best, even third best, but one of the best. So the ratio between cluster and between clusters, yes, it works most cases pretty well, and we are using it some cases. Some cases my students tend to use some other index, so I can point it out what are the best. So this is one of them. But it's not as trivial how exactly it should be done. But the principle is there, between cluster and between cluster. So measure the variance from point to its centroid, squared distance, sum it up. That we have the SSV. So basically, if you measure this for all points, so what this basically is, if I understand correctly, this is some squared errors, right? And then, this is a little bit more tricky because this can be measured in two different ways. This is the between clusters. So first, if you want to measure between cluster distances, so let's suppose here we have the cluster center points. Yes, they are here. And then what we have is the center point of the entire data. Centroid of the centroids. And if the centroids represent the center point of the clusters, so this centroid of the centroids is basically the center point of the entire data. So it's the average of all data points. Okay? Now, notice that what we are basically, so what I want to calculate is the distance, kind of the distance between the clusters. Now there is a relationship. In this sum of squared errors, if we take one cluster, and I calculate the sum of squared errors, so I need the average and I calculate the squared average distance of there, basically measuring the variance. Except I don't normalize it, I don't divide it by n, I just take the sum. So this is basically variance multiplied by the number of points. Then I have another way to do it. I can take all pairwise distances between the cluster. How much these points are from between each other. Now here I have n calculations to get it, and then if I multiply I get the sum of squared errors. If I take all pairwise distances, I will have n power 2 different. And if I take the average distance, okay, let's call it pairwise distance. So if I sum it up all of those, I have this many pairs to sum it up. And now here I have basically value that relates to n. It's not the average. If it's the average, if it's a variance, then it relates to it's the average per point. But now I have sum it up. I have the sum of the squared errors, sum of the whatever. So here, if I have now pairwise distances sum it up. So if I sum it up all the pairwise distances, I need to divide it by n. Then I get to the same scale. If I divide it by n power 2, then I have the average distance between the points, right? If I take this pairwise distances squared, what I have is average squared distances. In Euclidean space, this actually corresponds to the variance. So standard, yeah. I always a little bit confused about these exact equations, but that is what variance is. It is basically the average distance from the center points to others. But I can do also the between all pairs of points. And if I divide it to n divided by 2, I basically get the same result. this can actually, in Euclidean space, using squared distances, it is equal. So keep this in mind. Two different things measuring the same, or two different ways to measure the same thing. Now calculating this overall average of the data points. So yeah, if I want to calculate all pairwise distances of the centroids, again I have k centroids, I have k power 2 different distances. So if I calculate it, I get some result. Now if this result, if I divide it by k power 2, or if I get then I get the average distance of any pair. So based on that result, I can actually just calculate the distance to the center, data center. Sum it up, squared distances. Yeah, okay, here we have multiplied by the number of data points in each cluster, sum it up, but basically I get the same result. So basically this measure that I calculate all centroids distance to the data center point, it corresponds to calculating all pairwise distances. So that measures between clusters variation. Okay, I think you are looking, you try to look upside down or left or right and still can't really get it. It's difficult for me also to get it, but you just have to take my word on it now. So this is yeah. So the point is that we don't need to calculate, because if we calculate the all pairwise distances, it takes k power 2. We don't want to do that. We just calculate one center point of the entire data and then calculate the distance of that. It takes only k time. That's the reason why we use this equation instead of all pairwise distances. But you just have to understand that what this measures is between cluster distances, kind of average variation of it, except it sums up. So, and then need to sum it up and need to consider the scale. So this is very important to know that this n power 2, n or whatever, that they are on the same scale. Because what we are going to do, we are going to compare them. We are going to take a ratio between them or something like that. And if you compare something like the average distances to variance, variance is squared. If you're going to compare variance to something, sum of squared errors, it's n times. Variance is on average. So you have to scale them back to the same scale, otherwise, before doing any comparison. So these kind of tricks, or this understanding is needed before going to build any index. Okay, so the next what I have in the slide is this sigma x, and I don't have a clue what is it. And I don't like how it presented here, but let's see what comes out of it. So this basically now takes these two elements, the sum of squared within cluster and between cluster, and sums it up. If they are on the same scale, we have a two part of the equation, sum it up. Okay. Yes, we put them in the same equation, now we have one equation, and what happens? If we want to minimize the distance in the cluster, so we want to minimize this one, but then we want to put the clusters as far from each other, so we want to maximize that one. Linear equation, linear summation of two terms. One we want to minimize, one we want to maximize. Yes, let's try with different number of clusters, cluster it and measure the result. So with the correct number of clusters, we are expected to find the one that really, yeah, is it? No, okay. Okay, a little bit mysterious. So let's see what the, if the next equation makes more sense. Okay, now here. Okay, so this was sum up of the two SSV plus SSV. Now, if we minus SSV away from here, so what happens? They accumulate each other out. So basically, this part is SSV. Okay, just to make sure to, and okay, now let's see carefully. So what we are taking here is the ratio of the within cluster divided by and the between cluster. So now it becomes more like something we want to minimize, something we want to maximize. A little bit suspicious because then I put as many clusters as I want. And this we multiply by the number of clusters. Yeah, I don't know, can it really work? And this the VW index what we have, but okay, let's look here. We have the k times, sum it up the points. Okay, this is the Witting cluster. We sum it up n times, so there will be n elements multiplied k. So this is the number of distances we will have. And as a divider, we are taking now for every cluster. Okay, this 1 point. So every cluster, the Witting cluster distance multiplied by the cluster size. So the n becomes here because every cluster we sum it up. So this will sum it up to n in total. Yeah, so I still question why we need this kk, but it's, yeah. Okay, out of these elements now what was there are different variations, and it might actually be maybe if you have some exercise still coming to find out what would be your answer with this basic idea, with this component SSV, SSU, K, sigma, data centroid. Can you make more sense out of it, and what would be your result? Because this is what you can find literature, and they are not so convincing. Of course, they are pretty old. So knowledge has increased quite much since then, but surprisingly still open question that none of them is really the best possible solution. But Ball and Hall, first they use just the Witting cluster divided by k. Yes, this we want to minimize, and this yeah, well, it's a kind of penalty fact that the more we, because this we minimize, we just add more clusters, but then this will increase. Wait a minute, it's. Does it make sense?
Like the key somehow normalizes the effect of the SS level because we increase key. It's might be divided by key.
But SSV goes down the more we add k.
But the bigger the k, the smaller the error, and the bigger the k, the smaller the hole.
It sounds like you should
Make it more sense if we multiply.
Yeah,
but it's
yeah.
also not that good.
So why on earth they make this? It doesn't make sense. Yeah, multiply by k would make more sense already. So I'm missing something, or it's just people just try something and maybe it worked for some data or whatever. So I don't know. Okay, this I don't know what is this W here, k power 2, but Marriott 71, Kalinski, Harabash. Okay, this is already taking the ratio of these two. This makes already a little bit more sense, but because one we want to minimize, one we want to maximize, so actually I don't think they should be taking like that. They should be multiplied or something. But yeah, then there's this factor will because now this is divided. Actually, this is divided by that one, so it's normalized by the n minus k. Well, this is basically at the level of n, and then this is normalized by divided by k. So n is pretty much constant here. So this is odd n anyway. So I think it will be diminished in this equation, and then k. But this will, when we increase k, this tends to be increasing also, because this will actually go as divider. So the bigger the k, the smaller the value here. And what we want. So the bigger k, smaller this will become, but this we want to maximize, and this we want to minimize. So the bigger the k, how it goes, SSV between clusters, the bigger the k, it will become smaller. Yeah, so this will become smaller, this will become bigger. So overall this becomes smaller, and adding k here, so kind of the, yeah, so does this combination make more sense? Hartigan logarithm of the ratio, so the ratio seems to be pretty popular. Xu, okay, now we have already 97. Dimensionality times n power 2. This is now normalizing factor. This is like the sum of squared Witting cluster. So this is like the divided by n, make it kind of a mean squared error divided by dimensions. It's a normalized mean squared error, what we used a lot. except now the divided is once more and power 2. Taking square root logarithm of k, so yeah. So I can say it just looks pretty much like a mess. Okay, but I tried. This is also pretty old ratio. We actually for some reason call it as F ratio because it's pretty much, yeah, I think that's what it most resembles. So I divided this equation now with the three different terms. There's the divider, the between cluster, SSB. So I just clustered the data, don't remember which data, probably one of the S data sets, the between cluster SSB. When k increases, number of clusters increase, what happens? It doesn't change much. When we have very few clusters, then this number is somewhere, and then it starts to increase, but it's kind of stabilized. Increased number of clusters doesn't. So I suspect that if we increase the number of clusters big enough, it starts to go small as expected. But at this scale, what the number of clusters is pretty much constant. And that's one thing. Do we really need such a term in the equation anyway after all?
But if we are thinking about these variance between the clusters, the clusters usually need to cover the whole space.
Yes.
So it actually makes sense that it's kind of constant value.
Mm-hmm.
It doesn't matter if we have more clusters, then the average will be like still the same.
Yes.
So I'm not thinking if it's even like makes sense to consider this thing.
Yeah, the scale of the between cluster variances is much bigger. So I don't know, is the really the squaring that makes it happen? But intuitively, because that's what you want to do, you want to minimize this or maximize this between cluster variance, and then you want to minimize within clusters. So there's two terms that you want to do. But with this scale, because we have 15 clusters here, so with this adjacent area, it doesn't change much. So it doesn't contribute. And the other side, the within cluster, it's now I think it's a this term here, or MSE here, plus the k, which is kind of the scaling factor here, which are the denominator. So yes, the more clusters, they are also called, wait a minute, so denominator, so more clusters, the smaller it will become, so it's also supposed to go down, right? Okay, I didn't, I should have probably plot them separately, so the SSB is supposed to going down, but now it's multiplied by k. So k is giving penalty, so the more clusters we are giving the multipliers. So now the result you can see that actually what happens, there will be a key point, and actually it is a minimum point here. So this really indicates that this SSB isn't really needed in this equation. So SSB and just the k as themselves, but then it's very heuristic. They are not in the same scale and we are multiplying, and then we are minimizing that. Yes, with this kind of data set, it actually will find the minimum at the correct place, but where we need the SSB, so how we can benefit for that one. So that basically pretty much explains this we speculated already here that it should be multiplied, right? And that's what exactly I have there in the slide. So but we don't have exactly this same combination on these. So my point of view is that when we going to do some research or whatever, instead of just inventing something and proposing new method, it would be much better to actually analyze, divide it into smaller parts and to see what really happens. This is the only way to really learn. Okay. But this actually does work. So even with the SSB is pretty much constant, it is there in the equation. In my view, doesn't contribute that much. Okay, now notice some of my slides, the k is actually decreasing going to the right to the left, like this slide. So how this, and here we call it actually F ratio originally. So now I think this is the VP index of some of its variation, and should check it more carefully what is it. But this is what it goes. This is, okay, there are two different algorithms. But I think the random swap provides pretty much the same, so no difference. Yeah, it really goes down. There's one very small tiny knee point here, but here's a very clear knee point. And after that it's pretty much almost stable. Little bit increasing, but increasing big enough that we can able to detect the minimum point here. So it works. This is for S1. S2, same happens. S3. And even the most difficult S4. And now some small thing happens. This is the agglomerative clustering. This is an improved variant. There start to be a little bit more variation, and in fact, the agglomerative clustering here, it actually finds the minimum point at 16. So it already has big failure here, or small failure. The better algorithm still finds it here. So indicating if we don't have good enough algorithm, the algorithm may fool us, even if the index itself would work. As we see, good algorithm we get.
What's the ES?
So this is called iterative shrinking. This is Bränti Virmajoki 2007, I think, Vatta proposition or something. When I did the agglomerative clustering, it's kind of generalized variant. Agglomerative clustering, we have a merge of two clusters, so we merge them, and then we merge more. So iterative shrinking is basically, instead of merging, if we merge these two, we can consider it as a removal of one cluster. So if I remove that one and put all the vectors here, it's equal to merge. But who says I have to put all of them there? Maybe some of the vectors might join here, another cluster. So I break it. Some go there, some go here, and some go here. Effectively removing one cluster. More general than the merging. So it gives actually better result. Most cases no big difference, but in this kind of borderline cases, it does work better. So it's just one different algorithm, quite complicated, because how to calculate this kind of removal, you need to bookkeeping your nearest centroid and your second nearest neighbor, second nearest centroid. And when you do the removal, you have to lots of calculate which cluster you join, how to update this, how to update that. Quite complicated, so I don't really recommend unless you really care about it. Okay. So this is one summary. Okay. Data set. Oh yeah, this is S1, 2, 3, 4. So you can see all of these data sets are here. So how do you see some of the methods? Okay, like this. This one doesn't really solve anything. Ball and Hall, SSV divided by M also doesn't solve anything, so yeah, maybe just make a typo there, I should multiply. Logarithm of the ratio. Okay, now we see they start to be showing up 3 point. So it could be like the first step, and then some post-processing could be done, but still doesn't work. The ratio like this one here, yes, the same. 3 point can be clearly detected, at least some of them, the S3 and S4 is more here, but yeah, as a first, but only as a first step. Then this Xus method, again, yeah, clearly 3 point, but no minimum, no maximum, they are just not enough. So all what we find out that this combination did give the minimum in all cases at the correct location. So does it make sense or not, but this combination does actually work. At least for this data set. It doesn't work for every possible data set. The Birch is interesting cases, so I don't remember the result, but yeah. Okay, let's have a 8 minutes break here.